Max.
Ayan na.
Okay, good afternoon, class. Can you hear me clearly? Am I loud and clear? I can't read your chat straight from my screen. Okay. So we're going to discuss optimization today, and then tomorrow I will just be sending you the recorded video from my morning section on the topic of double integrals. So we will start with local extrema and the second derivative test. Our aim will be to find the local extreme values of a function of two variables. And unlike a function of a single variable, y equals f of x, whose graph is a curve in the two-dimensional plane, the graph of a multivariable function is a surface in the three-dimensional space. Okay. So now we're adding a third axis to our usual rectangular coordinate system with the x and y axis, so that instead of plotting just an ordered pair, we're going to plot an ordered tripole, so that if we collect all the points satisfying the given equation here, z equals f of xy, what we will have is not a curve, but a surface in general. So what do you mean by the local extrema of a function of two variables? Now, for a single variable function whose graph is a curve, we know that those are the high points and low points of the curve. And similarly, for multivariable functions, they will be also the highest and lowest points of the surface. So consider the figure here. We see two local maxima on the surface here and two local minima, the high points and the low points of the surface. They may not necessarily be the highest or the lowest points. They just need to be the highest or lowest points on a local region or part of the surface. So let's define more formally the meaning of the local extreme values of a function f of xy. So suppose again we are given a function whose equation is z equals f of xy, and we consider some point pq. Now, when is pq a local maximum of the function? If the function value of f at pq is always greater than or equal to the function value of all the ordered pairs or all the points on some in some region containing this point here, which I will illustrate later with a figure. Now let's define also the local minimum by just simply changing this inequality here. We have the following. We say that f of pq is a local minimum if its function value, okay, or the value of the function at pq is always less than or equal to the function value of all points in some region containing PQ. It does not have to be true for all the points on the domain. It just has to be true for some points in some region containing the point PQ here. Let's look at this graph. So here is the point PQ below on the XY plane, PQ. And then this is the point F at PQ, the point on the surface, okay, corresponding to the point PQ and F of PQ. So that PQ is like the projection of that point on the surface on the XY plane. Now, this is the region containing PQ. If we can find such region so that we get any point on that region, say this point here, and we evaluate the function at that point, we should get graphically a point that is lower than this point here corresponding to PQ for all points contained in this region. Now, it doesn't have to be true for the whole plane or the whole domain. It just has to be true for some region containing PQ, so that it's not an absolute maximum, but only a local maximum. Now, a similar geometric interpretation can be given to the local minimum value of a function, which we will not do here. Now, how do we find the local extrema of a given function of two variables? All we have to do is to observe that the plane tangent to the graph, okay, as shown here. So a while ago, this was the point that yields the maximum value, a high point on the surface given by the graph of z equals f of xy, and observe that the plane tangent to that point on the surface corresponding to PQ is horizontal. If you recall, if you have a local minimum or a local maximum on a curve that is for a function of a single variable, then the slope, or sorry, the line tangent to the curve at the high points or the low points of the curve will always be horizontal. However, for a surface, we have a plane now instead of just mere tangent lines. So the plane tangent to the surface at a high point must be horizontal, and also, of course, for a low point on the surface. Now, this means also that the tangent lines given by these two intersecting lines here in the direction of the x and y axis must also be horizontal, since they lie on the tangent plane as well. Remember, when we were discussing partial derivatives, we said that the derivatives represent the slopes of the lines tangent to the surface at the point of tangency in the direction of the x and y axis. So here in the figure, since PQ is a high point, they will be horizontal. And since the partial derivatives give us the slope of the tangent lines, then that means the partial derivatives with respect to x and with respect to y, sorry, there's a typo error here, at PQ must both be equal to 0 since they are horizontal. So we have the following result. So let f of AB be a local extremum for the function f. Then, okay, by the way, when we say extremum, we mean either a minimum or a maximum. So suppose f of AB is a local extremum for the given function, then if both the partial derivatives with respect to x and with respect to y exist at the extremum, what we know is that the following equations follow. The partial derivative with respect to x at that extremum will be 0, and also the partial derivative with respect to y at that extremum is also 0. Now, the converse may not necessarily be true. It does not mean that if the partial derivatives are 0, then we always have a local extremum. There are cases where we can have the two equations here satisfied, but we neither have a maximum or a minimum point at the point AB. And such points are what we call saddle points for a surface. And that's the equivalent of inflection points for curves. Remember, what is a point of inflection? It's neither a high point nor a low point. It's not a maximum nor a minimum, but still the tangent line at the inflection point is horizontal. So we have also saddle points for a two variable function where we can have the horizontal lines, the tangent lines horizontal, but we neither have a local maximum nor a local minimum there, as illustrated in this figure here. Look at the point there, which just sort of sits on the surface, and we have a saddle-like shape near that point, and that's why it's called the saddle point, as in the saddle of a horse. And we say that this is a saddle point because if you draw the uh, tangents to that point in the direction of the axis, then they are horizontal. But we neither have a maximum nor a minimum at that point. So that means we need an additional criteria for determining the local extrema of a given function. Well, the candidates, of course, we know from the previous result are those points for which the partial derivatives are both 0. However, since not all of them will automatically be a local extremum, then we devise some tests to determine which of them will be an extremum, which of them will be saddle points. And that's what we call the second derivative test. So it goes as follows. Suppose that AB is a critical point, meaning the partial derivatives, okay, let's go back. Okay, the partial derivatives are both 0 at the point AB. So we call that point a critical point, just like in single variable calculus where the derivative is 0 or undefined, but we will not be including here where the partial derivatives are undefined. So again, suppose we have a critical point AB. How do we know if this critical point gives rise to an extremum or a saddle point? Now consider the second order partial derivatives A, B, C. Now A here is the second order partial derivative of the function with respect to x. B is the cross derivative with respect to x and y. And C is the second order partial derivative with respect to y at the given critical point AB. Now let's have the discriminant defined as follows. D is equal to the product of A and C minus the square of B. So it's the product of the two second order partial derivatives with respect to x and y minus the square of the cross derivative. Now we have four cases. Case 1, the combination D, A are as follows. D is positive, A is negative. Then what we have is a local maximum. Remember in single variable calculus, when the derivative is negative, the second derivative is negative, that means the graph will be concave upwards, and so we will have a local minimum. It's like the this one is like the parallel to that. However, we are dealing now with partial derivatives. And case 2 is we also have a positive D, but this time we also have a positive A. Then f of AB will be a local minimum. So that we have two cases left where either D is 0 or D is negative. Now, what if D is negative? Then whatever A is doesn't matter. As long as the discriminant is negative, we always conclude that the point AB gives rise to a saddle point, or there's a saddle point at AB. And if D is 0, then there's no use using the test. The test fails. We cannot determine anything. So let's illustrate the theorem. let's consider this function here, x squared plus y squared plus 2. And graphically, we just translate this circular paraboloid because its horizontal cross sections are circles while its vertical cross sections are parabolas, so it's called a circular paraboloid. You have here the graph of the paraboloid x squared plus y squared. So you just add 2, so that means you just translate this 2 units upwards and you have the graph of the given function here. I can't find a graph in Google that gives me exactly the graph of this one. So I just put this one here and you just imagine translating it 2 units upwards. Now, obviously, there will be a minimum at 0, 0, and the minimum value should be 2. Notice that these are squares, and we know that the square of any number is non-negative, so that this result is at least 2. 0 plus 0 plus 2. That's as small as it can get. And it happens if both x and y are 0. So let's apply the second derivative test. That's the given function. Yes, do you have a question? No question? So let's continue. So we have here the function, and step 1, we get the critical points. Again, the critical points are where the partial derivatives with respect to x and y are both 0. So we get the partial derivative with respect to x. And if you look, it will just be 2x. And the derivatives of the last 2 terms will be 0 with respect to x. And we equate that to 0. Similarly, we get the partial derivative with respect to y. And this will become 0, 0. So we just have 2y. And we solve for x and y. And obviously, we get x equals 0 and y equals 0. So what do we have here? Only one critical point. As observed before, okay, this verifies that the second derivative test is accurate. So we have a critical point at 0, 0, the only critical point. Now we are ready to compute the values of a, b, c, and the discriminant d. Again, for step 2, compute the cross derivative, the second order derivatives. So let's just bring back fx and fy here. Then we get the cross derivative, the second order derivatives. Now, if you differentiate this with respect to x, it's just 2 for fxx. So we plug in the critical point 0, 0. And since it's just a constant, then that means at 0, 0, the value is also 2. Again, we get the cross derivative fxy. So we differentiate this one with respect to y. And since x is treated constant, so it's 0. It's constant. Whatever x and y are, the value of this function is always 0. And thus, at 0, 0, it's also 0. Now, we get fyy. And that means we differentiate this one with respect to y. So that will be 2. And thus, at 0, 0, it's also 2. So those are the values for a, b, and c. Now, we compute the discriminant ac minus b squared, plug in those values, we get a positive value of 4 for d. So what we need to do now is observe the signs of a, which is 2, positive, and sign of d, 4, which is also positive. So what do we have here? We classify the critical points. Both are positive. That falls under case 2. So we have a local minimum. If they are the same in sign, I mean, if they are both positive, we have a local minimum at the critical point. So that is verified by the graph of the surface, which is a circular paraboloid with vertex at 0, 0, 2. Again, that opens upwards. So do you have any questions so far on the second derivative test before we illustrate it again with another example? Okay, then let's consider the two variable function here. F of xy equals negative 2x squared plus xy minus y squared plus x plus 5y minus 8. Now we're going to find the local extrema. Step 1 again, find the critical points. Okay, here we get the partial with respect to x, and we differentiate this negative 4x with respect to x. That's why this is 0, this is 1, this is 0, 0, and we equate to 0 the partial with respect to x. And all you have to do is, whenever you get a linear equation, you solve for one of the variables, say y, in terms of x. So we have this one. You can just verify that. So we proceed to the partial with respect to y. We get 0 for this one, and then x. Then for this one, negative 2y, 0 for this, 5, and 0. And then we equate that partial to 0. And then again, we solve for y. We get that. Now, to solve this system, all you have to do is equate the two here. So giving us that equation, which can be solved for x, it's just a simple linear equation that can be done by multiplying by 2, combining x on one side, and verify that you will be getting x equals 1. And once you have gotten the x value, all you have to do is use either of the two equations here, plug in x equals 1, and you should get y equals 3. So that means we got only one critical point whose coordinates are 1 and 3. So we only have one critical point to test. So let's use the second derivative test. Compute ABC, then the discriminant. Again, the first order derivatives are there. Let's find f x x. So we differentiate this with respect to x. We get negative 4. And again, the value at the critical point will be negative 4. Now, it's not always the case that you will get a constant value for the second order derivatives. In the exercises I gave in the problem set, you will encounter there problems where you get an expression for the second order derivative. So you have to plug in x equals 1, y equals 3 into the expression or formula for the second order derivatives. Now fxy, we differentiate this with respect to y, so we get 1. So at 1, it's 1. And then second order with respect to y, we differentiate this with respect to y, we get negative 2. So at 1, 3, it's negative 2. And then the discriminant AC minus B squared will be positive. And note that A is negative. So what do we have? D is positive, A is negative, so that's case 1. And therefore, we have a local maximum at the point 1, 3. So the coordinates will be, okay, an ordered tripole with coordinates 1, okay, for x, 3 for y, and 2 for z. So that's where we have the local maximum point. Now we call to the local maximum value. Any question on this? So let's have an application on optimization. Word problem here. Let's read. Find the dimensions of the rectangle with a perimeter of 20 units if its area is a maximum. So we want to maximize the area, but we are given that the perimeter, no matter how we construct this rectangle, is fixed at 20 units of measure. So let's begin by assigning variables to the dimensions of the rectangle as usual, x and y, length and width. Then how do we get the perimeter? It's 2 times the length plus 2 times the width. So that will be 2x plus 2y. But we are told that its perimeter is fixed at 20, so we set that equal to 20, giving us a relation between x and y. Now, what we do in single variable calculus is, okay, before we use the second derivative test for two variable functions, so here, what we do is solve for y and then formulate a single variable function representing the area. The area is, if we denote it by fxy, is length times width. So it will be x times y. And we got y here in terms of x, so we can plug that in here to give us this one, which if simplified gives us the quadratic function 10x minus x squared. And recall, in single variable calculus, all you have to do is get the critical point or points of this function, and you do that by setting its first derivative to 0. So differentiating this one, 10 minus 2x, we equate it to 0. We solve for the critical points, the x value, we get 5. And then from the relation here, y equals 10 minus x, we plug in x equals 5, we also get y equals 5, as simple as that. So our answer is that the rectangle is a 5 by 5 square. That rectangle has the maximum area of 25 square units, 5 times 5. However, we can also use the second derivative test for a multivariable function, because if you observe, f of xy here is a function of two variables, although we converted it into a single variable function. But sometimes this cannot always be done, especially if solving for y in terms of x or x in terms of y would be, if not impossible, complicated. So instead, we use the second derivative test as follows. Okay, sorry. We are dealing now with the method of Lagrange multipliers. By the way, I won't be giving you problems. I did not give you problems on optimization problems, word problems for the second derivative test. So, okay, the method of Lagrange multipliers, if you saw the module, okay, has basically 4 steps, and it's a very powerful method for solving optimization problems, named after Joseph Lagrange, French mathematician who first discovered the method. And instead of giving you or listing down here the steps right away, so I'll be listing it down one at a time and then applying it to the present problem. Now, for step 1, all you have to do is formulate the problem. What do we want to maximize? The area. And the area is represented by this two variable function f of xy, length times width, xy. Now below, we have what we call the constraint g of xy. And where did this constraint come from? Let me go back a few steps. It came from this one here, where we know that the perimeter is 20, and in terms of x and y, it's 2x plus 2y. And all we did was to transpose 20 to the other side so that we always have a 0 on the other side here. So 0 on the one side. So that this one here, this expression on the left-hand side will be the constraint function g of xy. And using these two functions f and g, we can construct for step 2 the what we call Lagrange function. So it's given by, generally, capital F, that's the Lagrange function, which is a function of three variables, x, y, and lambda. And lambda here is called a multiplier, and hence the name Lagrange multipliers. And it's constructed by adding the function to be optimized plus the constraint function times the multiplier lambda. So if we're going to plug in these two in this formula, we get our Lagrange function as xy, that's f plus lambda g. So we have this one. That's our Lagrange function. So this is the formula for it. And you just have to get those from step 1, where you first, of course, formulate the quantity to be optimized in terms of a two-variable function. And then you have to determine the constraint based on the given in the problem. So let's proceed to step 3. Now for step 3, it's almost the same as the second derivative test. And we simply have to find the critical points. And since the Lagrange function is a function of 3 variables now, we just have to set each of the partial derivatives with respect to x, y, and the recently introduced variable, the multiplier lambda. Just set them all equal to 0, and we have the critical points. So let me show how to get them, given the problem. This was the Lagrange function a while ago. We get the partial derivative with respect to x. So let me just explain why it became like this. Well, if you're differentiating with respect to x, all other variables will be treated as constants if they are independent variables as well. So capital F is the dependent variable. It depends on the 3 independent variables x, y, lambda. So if we differentiate with respect to x, y, and lambda will be treated as constants. So we differentiate this with respect to x, we get y. And then lambda is a constant, so times the derivative of this with respect to x, so this has a derivative 0, this has a derivative 0, and the derivative of 2x with respect to x is 2 times the constant lambda. That's why we have this one. And we equate it to 0. And then we solve for y in terms of lambda. And that will be the usual approach. In the next steps, you will be solving for the other variables in terms of lambda as well. But we only have one more. Although in other problems, you might also have x, y, z. So with lambda, you will have 4. Now, we get the derivative with respect to y of this one, that's x. Derivative of this with respect to y is 2. 0 here, 0 for this one, times lambda. So we get this. We equate to 0. And then we solve for x. Excuse me for a while. Okay, let's continue. And then we differentiate with respect to lambda. And since the other variables will be treated as constants, so the derivative of x and y are both constants. So this will 0 out. And this lambda, this expression beside lambda is also a constant. No lambda here, only x and y. So we just differentiate lambda times this constant, and the derivative of lambda with respect to itself is 1 times this. So we just get the constraint. You always get the constraint whenever you differentiate with respect to lambda. So we equate that to 0. We get the constraint equation as before, 2x plus 2y minus 20 equals 0. And we solve this system. Now you look at the system for a while. 3 equations in 3 unknowns. How do you solve for the critical points? Well, since we've already gotten x and y from the first 2, so what we can do is plug in into the x and y in the third, so that we will be solving for lambda. So I'll replace x by negative 2 lambda, y by negative 2 lambda. In this one, we have that. Okay. And all you have to do is solve for lambda. It's just linear in lambda. You get lambda, just verify, equal to negative 5/2. And once you've solved for lambda, you can get x and y from the first 2 here. Since lambda is solved, So we get x equals y are both negative 2 lambda, and we plug in lambda, we get 5. So we get the same answer as before using single variable calculus, this time now using Lagrange multiplier method for multivariable calculus. So same answer, 5 by 5 square. And as I have said, this can be applied to any number of variables. So you can have like a 3-dimensional problem, like the volume of a box, and you might have x, y, z, and then you have to introduce the multiplier lambda. So you will have the Lagrange function capital F in terms of x, y, z, lambda. So you will be differentiating it with respect to 4 variables. And you can always extend it to any number of variables. Okay, who has a question?
Sir,
Yes.
why do we have to introduce lambda?
Sorry, can you
Why
speak
do we have
louder?
why do we have to introduce lambda?
Um, well, it's a technicality. It's not that explained in the book, but lambda was introduced. There's a theorem there so that we will get the critical point always, even if we introduce lambda. And so that we always have the constraint equation satisfied. If we go back, okay, here, for the Lagrange function, this is what you want to maximize, right? And this is the lambda variable that was introduced times the constraint. So the thing here is that if you differentiate it with respect to lambda, you always satisfy whatever critical point you get, you will always satisfy the constraint. And moreover, since it satisfies also the fact that the first order partial derivatives with respect to x and y are 0, what we get from this system will also be a critical point for this that satisfies the constraint equation. Okay, is there any more question? Now, in the problem set, there is one there where you have to use x, y, z, lambda. So you just extend this to 3 variables. So partial with respect to x, partial with respect to y, partial with respect to z, and then partial with respect to lambda, and then you solve the system. 4 equations, 4 unknowns. Now, as what the other teachers do, they actually don't teach all of the stuff. So they leave some things for the students to research on. And I think some of them construct their own problems where you have to make decisions based on the tools taught you in the module. But I've decided just to give you the problems in the book. So I think this is the last example. And there's another one. Let me see it after this. So let's have the problem here. So sometimes you're directly given the optimization problem. So minimize this function in x and y subject to this constraint. Lagrange function. This is the function f, small f. This is the constraint with this 25 transposed to the other side. Then times the multiplier lambda. Differentiating with respect to x, that's 10, 0, and then 2x times lambda, 0, 0. So we have this. Equate to 0, solve for lambda, solve for x, we get negative 5 over lambda. Similarly, derivative with respect to y is negative 2y plus 2 lambda y. 2y, y squared as derivative 2y. Now, however, here you cannot solve for y as you solve for x because it's not one that you can just divide by something to get y, because you lose some of the critical points. I will explain. Now, if you look at this derivative, you can factor it out with respect, factor y out, getting this one. And if you equate it to 0, notice it's a product. So when a product is 0, remember, one of its factors must be 0. So we have several cases. Case 1, this is 0, or case 2, this one is 0. Now, if we consider those, if we equate this factor to 0, that gives us lambda equals 1. If we equate this one to 0, that gives us y equals 0. So we will be dealing with these two cases after. Let's first get partial with respect to lambda, and that's the constraint, equal to 0, getting this one again. Case 1, y equals 0, then we will do case 2 here, lambda equals 1. So if y is 0, considering this one, what you can do is plug in y here to get x. So if you plug in y equals 0 here, you get x squared equals 25, giving you two possible values for x, plus minus 5. So don't forget, when you have a square equals positive number, you get both of the square roots. So that gives you, with y being 0 and x 5, negative 5, that this case will give you 5, 0, and negative 5, 0 as critical points. Now, if you look back here, we consider the other case for this one, lambda equals 1. Okay. And what we will do is get x straight from this one. Since lambda is 1, then we quickly get x equals negative 5. Let's look at that here. Case 2. So this was, again, the derivative. If x is negative 5, so we'll get y equals 0. All right. So if you got confused, let me go back. So we have lambda equals 1 again. If you plug in lambda equals 1 here, x is negative 5. And if you plug in negative 5 here, negative 5 squared is 25 minus 25. So y squared equals 0. So you'll be getting y equals 0. So you get the same critical point. So no additional critical point was gotten. Next, we evaluate at each critical point. Now, here's the thing. What, sir, if we have many critical points? Then evaluate the function to be optimized, not the Lagrange function, but small f, the function to be maximized or minimized. And choose the highest value. This is like your second derivative test in single variable calculus. The highest value will give you the local maximum value, and the smallest, the local or a local minimum value. So evaluating at each, we have the following results. At 5, 0, it's 50. Okay, dito ko siya pinalagin. Dito sa f of xy, not capital F. So this is what you want to minimize. So that's where you plug in. So doing so gives us, again, 50 and negative 50 for 5, 0 and negative 5, 0 respectively. So actually, this gives us more than what is asked in the problem, which is it to minimize, or anyway, this gives us the local maximum value, and this one gives us the local minimum value. Is there any question? Okay, last one. Word problem. Okay, a box with open top and a volume of 256 cubic centimeters is to be constructed such that its base is a square. Find the dimensions of the box with the maximum surface area. Here's the figure. So square base, that means we can let x be the sides of the square base. So y the height. So we need only two variables instead of 3x, y, z. Now, if it's not stated that it has a square base, then you have to use x, y, z, and that means you have to extend the method of Lagrange multipliers to 4 variables, x, y, z, lambda. But again, here we only need 3, x, y, lambda. Now, this is the function to be maximized. This is the surface area. How do you get the surface area? You add up all the areas of the sides and the bottom. No top, open top. So we know that the bottom here has area x times x, square base, side x. And then these two sides, the left and right sides, each have an area of xy. So twice, we get 2xy. And as well as for the front and back faces or sides. So this one has an area x times y again. So twice, we get another 2xy. So in all, we have 4xy plus x squared, the bottom. So this is the function, if correctly formulated, okay, to be optimized. Notice, if you get this wrong, then you'll have everything wrong after. Now, what's the constraint? How do we get it? From the fact that the volume is 256 cubic centimeters. Now, what's the volume of a box? Length times width times height, x, y, z. Or rather here, x times y. So x squared y. And we set that equal to 256, the given. So now we can form the Lagrange function. Maximize f x squared plus 4xy subject to the constraint g of xy equals x squared y minus 256 equals 0. Applying the method, we form the Lagrange function. This is small f, this is g of xy. So the rest would be to get the critical points by equating each derivative to 0. Now verify, okay, that you'll get the following partial derivatives with respect to x, y, and lambda, and you equate each of them to 0. Now let me just explain how to get or how to solve the system. Okay, looking back at the second equation, try to factor this out mentally. You factor out x, you'll get 4 plus lambda x. So we have this, right? Just anyway, this will be uploaded. If you can't get it quickly the first time, then you can just go back to that point on the video. So anyway, you should be getting this when you factor it out and you equate it to 0. And that gives you two cases. Set each factor to 0. You have this. So x equals 0 or x equals negative 4 over lambda. Now I will eliminate this one since we are dealing with a dimension. There's no 0 length or width or height. So that means we only have one case. Of course, if this were not a real word problem, okay, you would have to consider both cases. But again, dimension is non-zero or positive. So that means we have to set x equals negative 4 over lambda. Now here's the first of the equations in the system. And what we do is plug in that expression for x. We replace this x's by negative 4 over lambda, and just note, we should have this. Let me just explain. This x, if replaced by negative 4 over lambda, will become negative 8 over lambda. Then copy the 4y. And then replace this x by negative 4 over lambda. Lambda will cancel out, leaving you with negative 8y. So 4y minus 8y is negative 4y. And if you solve 4y, you'll get negative 2 over lambda. Now observe so far, we have x in terms of lambda and y in terms of lambda as before. So that's the usual thing you do. If you have a system, solve for each x and y. Okay, if there's a z, each variable in terms of lambda. And then plug into the constraint equation. Okay, where did this come from? Came from the constraint. X squared y minus 256 equals 0. So you plug in the expression for x and then for y in terms of lambda here. So this is x squared and then y. And the rest is algebra. You should get negative 32 over lambda cubed for this one. And then if you solve for lambda cubed, transpose, cross, multiply, you'll get this. And then you take the cube root, lambda equals negative 1/2. And if we have lambda, since we have x in terms and y in terms of lambda, we can just plug in to get x equals 8, y equals 4. So problem solved. That means the square base has a side of length 8 units or centimeters in this problem, and the height is 4 centimeters. So dimensions 8 by 8 by 4. So does anybody have a question? Now, listen. For the word problem, only the leader needs to submit. But I will be giving you a grade individually. Although the other members won't be submitting, you'll be receiving the same grade. Are there other questions regarding the discussion or the problem set? Deadline will be last day of finals week. Is it Friday or Wednesday?
Wednesday, sir.
Wednesday. So 5 p.m. of the last day of the finals week. Now, I will still be available for consultation, but it has to be by appointment. Now, you cannot ask me directly, of course, the problems in the exercises. So I will just be giving you the concepts you need, but not, I will not be solving a problem even similar to the problem. Okay, so that's it for today. Sorry, tomorrow wala tayong class. I-upload ko lang yung session ko sa umaga.